Hi, so today we're going to go over curve sketching, and the function that we're going to graph is f of x is equal to the quantity x minus 4 squared over x squared minus 4. We're going to try to graph that using things that we learned from calculus. So we start off with the domain, and that's when the denominator is equal to 0. So we're going to take the denominator of our function, which is x squared minus 4, and set that equal to 0. So we're going to add 4 to both sides, and once we do that, we're going to get x squared is equal to 4. Now we're going to take the square root of both sides to get x alone, and when we do that, we get x is equal to plus or minus 2. Now those numbers are going to be when our function is undefined, saying that those are the numbers that control our domain. So when we write our domain, we're going to start from the number negative infinity, which is to say that all negative numbers are going to be included, up until we reach the number negative 2. And we're going to use parentheses to say that negative 2 is not included. So we're going to move on to say that negative 2 and 2 is also part of our domain, and 2 to infinity is part of our domain. So this is all one long domain statement. Now we're going to move on to intercepts, which is when the graph hits the axes. When we're solving for x-intercepts, that's when our function is equal to 0. So we're going to set our function equal to 0. So we're going to write 0 is equal to the quantity x minus 4 squared over x squared minus 4. We're going to multiply both sides by x squared minus 4. And when you multiply something to 0, it's still 0. So that's going to give us 0 equals the quantity x minus 4 squared. We're going to take the square root of that to get rid of that second power. And of course, when you take the square root of 0, it's also 0. So you get x minus 4 is equal to 0. So you add 4 to both sides, and you find that x is equal to 4. And that's going to be our x-intercept. When we move on to y-intercepts, that is when we have x equal to 0. So we're going to take our function, and everywhere that we see an x, we're going to replace it with 0. So we're going to write y equals the quantity 0 minus 4 squared all over 0 squared minus 4. And when we do that, we're going to see that we get negative 4 squared over negative 4. And that's just going to end up being 16 over negative 4. And when you simplify that, you're just going to get negative 4. Which just means that y is equal to negative 4. And that's going to be when your curve or your graph is going to hit the y-axis at negative 4. Next, I'm going to talk about our third step, which is symmetry. Now we have both even and odd functions, and sometimes a function is neither even or odd. Now an even function is symmetric about the y-axis, which means when you plug in a negative x value into your function, you're going to get the same positive y value as if you had plugged in a positive x. An odd function is symmetric about the origin, which means when you plug in a negative x value, you're going to get a negative y value, which is the opposite of what you would get if you had a positive x value. Now this is just going to dictate what our graph is going to look like. Now we're going to see if our function has symmetry. So what I'm going to do is I'm going to plug in 1 and negative 1 into our function and see what kind of y values we get. So we're going to take f of 1, which is just going to be the quantity of 1 minus 4 squared all over 1 squared minus 4. And that's just going to give us negative 3 squared all over negative 3. And we just get 9 over negative 3, which is going to give us a y value of negative 3. And when we plug in f of negative 1, which is what we're going to do next, we're going to see that the quantity negative 1 minus 4 squared all over negative 1 squared minus 4 is going to be equal to negative 5 squared over negative 3, which is going to be 25 over negative 3, and it's just going to give us a y value of negative 25 over 3. Now we see that that means our function has no symmetry. I'm going to explain why that is. Negative 3 and negative 25 over 3 are neither the same number nor opposites, which means that our function is not going to be symmetric about the origin nor about the y-axis. Next, I'm going to talk about asymptotes, which is when our graph is undefined. Vertical asymptotes are when the denominator of our function is equal to 0. So we're going to set x squared minus 4 equal to 0. We're going to add 4 to both sides, and that's going to give us x squared is equal to 4. Now we're going to take the square root of both sides, and that's just going to give us x is equal to plus or minus 2. Now we're going to move on to horizontal asymptotes, which we find when we take the limit of the function as x approaches infinity. Now we're going to write that as the limit as x approaches infinity of our function, which is x minus 4 squared all over x squared minus 4. Now when we multiply out our x minus 4 squared, we get the limit as x approaches infinity of x squared minus 8x plus 16 all over our denominator, which is x squared minus 4. Now we're going to use a theorem that states that if r is greater than 0 and is a rational number, then the limit as x approaches infinity of 1 over x to the r is equal to 0, which means that we can multiply our function by a fractional form of the x with the highest power. Now, since we do have to multiply by 1, we're going to do this to both the top and the bottom of our function. Now when we do this, we get the limit as x approaches infinity of 1 minus 8 over x plus 16 over x squared all over 1 minus 4x squared over x squared. Now, according to our theorem, we can take anything over an x to 0, leaving us with just 1. And that's going to be our horizontal asymptote. Now what we're going to do next is take the first derivative of our function, and that's going to give us the intervals of increase and decrease in our graph. We're going to write that as f prime of x, and we're going to use the quotient rule to take the derivative of our original function. So we write that as x squared minus 4 times 2 times the quantity x minus 4 times 1. And from that, we're going to subtract the quantity x minus 4 squared times 2x. And all of that is going to be over a denominator of the quantity x squared minus 4 to the power of 2. Now when we simplify that a little bit, we're going to get 2 times x minus 4 times x squared minus 4 minus the quantity x minus 4 squared times 2x, all over the same denominator of x squared minus 4 squared. Now what we can do from here is factor out an x minus 4. So you're going to get 2 times x minus 4 times the quantity x squared minus 4 minus x times the quantity x minus 4. And all of that is going to be our denominator of x squared minus 4 squared. Now when we simplify that, we're going to get 2 times x minus 4 times 4x minus 4 all over that denominator of ours, which is still x squared minus 4 squared. Now what we can do is factor out a 4. So we're going to get 2 times x minus 4 times 4 times x minus 1 all over our denominator, x squared minus 4 squared. Simplifying that one more time, we're going to get 8 times x minus 4 times x minus 1 all over the quantity x squared minus 4 squared. And we're just going to leave that like that. And that's going to be our first derivative, f prime of x, of our function. Now what we're going to do now is find our critical numbers, which is when the denominator of our derivative is equal to 0 and when our derivative is equal to 0. So what we're going to do first is set our derivative equal to 0. That's just going to be our derivative, 8 times x minus 4 times x minus 1 all over x squared minus 4 squared. And we're going to multiply both sides by x squared minus 4 squared. And that's just going to give us 0 is equal to 8 times x minus 4 times x minus 1. When we divide that by 8, we get x minus 4 is equal to 0 and x minus 1 is equal to 0. And that's just going to give us x values of 1 and 4 after we add 4 to both sides on one side and add 1 to both sides on another side. Now what we're going to do next is set our denominator equal to 0. So that's going to look like x squared minus 4 squared equal to 0. And we're going to solve for x. So we're going to take the square root of both sides to get rid of that second power. That's just going to leave us with x squared minus 4 is equal to 0. And then we add 4 to both sides, and we just get x squared is equal to 4, and we take the square root again to get an answer of x is equal to plus or minus 2. Now we're going to use those numbers and make a sign chart to find the intervals of increase and decrease in our graph. So what we're going to do is draw a line, and we're going to place the numbers -2, 1, 2, and 4 onto this line. Now to the side of this sign chart, we're going to write the parts of our function that correspond to each of these critical numbers. So 8 times x minus 4, x minus 1, and 2x squared minus 4s. And the reason for that is because in our denominator, we have x squared minus 4 squared. And all the way at the bottom, we're going to write our total derivative, f prime of x. And we're going to draw some lines on our sign chart to correspond to different intervals. And those are the intervals between each of these critical numbers. Next, we're going to write zeros on our sign chart corresponding to where the critical numbers are zeros in the functions. And then, by plugging numbers into our functions, we're going to find the intervals of negative and positive. So we're just going to plug in numbers in between each of these intervals. And as you can see, what I'm doing here is I'm marking negative signs for when our function is going to give us negative values and positive signs for when our function is going to give us positive values. Now what we're going to do next is multiply and divide these values out as if we were multiplying or dividing real numbers. So a negative times a negative is going to give us a positive, and a positive over a positive is a positive, and so on and so forth for all of these intervals. So you see that we get a positive, a negative, and a positive. Positive values means that those are intervals in which our graph is increasing, and negative values is going to be when our graph is decreasing. So when we write these out as intervals, we're going to get an interval between negative infinity and negative 2 of increase, an interval between negative 2 and 1 of increase, and an interval between 4 and positive infinity of increase. And we get an interval between 1 and 2 of decrease, and an interval of 2 to 4 of decrease. And those are going to be our intervals of increasing and decreasing values. Now we're going to move on to which of these numbers are going to be minimums and maximums of our graph. So we have x equals 4 and x equals 1. As you see, as I've written here, that 4 is a local minimum because it is between a decreasing and an increasing interval. And 1 is a local maximum because it's between an increasing and a decreasing interval. And I'm just going to plug those numbers into our function to find out what their y values are so we can get a point. Now as you see from what I've written here, that negative 2 and 2 are undefined according to our original domain. So we can just ignore those when we're trying to find local maximums and minimums. So when I plug in 4 into our function, I get a value of 0. So the point 4, 0 is going to be our local minimum. And when I plug in 1 into our function, I'm just going to get a value of negative 3, making the point 1, negative 3, the local maximum of our function. So what we're going to do next is take the second derivative of our function, which is going to give us the intervals of concave up and concave down of our graph. So we're just going to write that as f double prime of x and use the quotient rule on our first derivative to get our second derivative. Now when we do that, we're going to get x squared minus 4 squared times 8 times 2x minus 5 minus 8 times x squared minus 5x plus 4 times 2 times x squared minus 4 times 2x. And all of that is going to be over a denominator of x squared minus 4 to the 4th power. Now what we can do from here is factor out a 2 and an x squared minus 4. So what that's going to look like is 2 times x squared minus 4 times 4 times x squared minus 4 times 2x minus 5 minus 16x times x squared minus 5x plus 4. All over our denominator. And what we can do now is cancel out that x squared minus 4 on the top and take this denominator now to the 3rd power. And we move on to simplifying this some more. We're going to get 2 times 8x to the 3rd minus 20x squared minus 32x plus 80 minus 16x cubed plus 80x squared minus 64x, all over our new denominator of x squared minus 4 to the 3rd. Simplifying that down some more, we're going to get 2 times negative 8x cubed plus 60x squared minus 96x plus 80, all over our denominator of x squared minus 4 to the 3rd power. Now what we can do from here is factor out a 4. So simplifying our function some more, it's going to be 2 times 4 times negative 2x cubed plus 15x squared minus 24x plus 20, all over our denominator, which is still x squared minus 4 cubed. And finally, we just multiply that 2 and 4 together to get 8 times the value inside of our brackets, negative 2x cubed plus 15x squared minus 24x plus 20, all over our denominator of x squared minus 4 cubed. And that is going to be our second derivative, or f double prime of x. Next, we're going to find the critical numbers of this second derivative. So we're going to set our derivative equal to 0, and that's just going to give us 8 times negative 2x cubed plus 15x squared minus 24x plus 20, all over our denominator of x squared minus 4 cubed. We're going to multiply both sides by our denominator to eliminate it. And when we do that, it's just going to give us 0 is equal to 8 times negative 2x cubed plus 15x squared minus 24x plus 20. And we divide that by 8 on both sides. And we're just going to get 0 is equal to negative 2x cubed plus 15x squared minus 24x plus 20. When we solve for x, we're just going to get x is equal to 1/2 times 5 plus 3 times the cube root of 3 plus 3 to the 3/2 power. And when we solve for x, we're going to get a number around 5.7034. Now when we set our denominator equal to 0, which is just going to be x squared minus 4 cubed, set equal to 0, we take the cube root of both sides, which is just going to give us x squared minus 4 equal to 0, add 4 to both sides to get x squared is equal to 4, and take the square root of both sides to get x equal to plus or minus 2, once again. Now what I'm going to do next is make a sign chart for this derivative. And I'm going to set it up in much the same way as I did before, with the parts of our function on one side, and our critical numbers on the sign chart, and our second derivative on the bottom. And I'm going to mark zeros where the critical numbers correspond to zeros in the function, and I'm going to make lines in the chart to separate it out. Now once I've done this, I'm going to fill in my sign chart corresponding to positive values and negative values between my intervals. And I'm going to see what they end up looking like in my second derivative. Now, as you can see, I've got a positive, a negative, and a positive and a negative. Positive values are going to correspond to intervals of concave up, and negative values are going to correspond to intervals of concave down in our graph. So between negative infinity and negative 2, we have an interval of concave up. And between 2 and our x value of 5.7034, we have another interval of concave up. And between our value of negative 2 and 2, we see that we have an interval of concave down. And between 5.7034 and positive infinity, we have another interval of concave down. So next we're going to talk about inflection points. Since negative 2 and 2 are undefined, we're going to ignore them still. And x, which is about 5.7034, is an inflection point because it's between an interval of concave up and an interval of concave down. So we're just going to plug that into our original function to find its corresponding y value. So f of 5.7034 is going to be equal to 5.7034 minus 4 squared all over 5.7034 squared minus 4. And when we evaluate that, we get a number slightly larger than 2.9 over a number that's slightly larger than 28.5. And when we evaluate that, we get a number around 0.1 as our y value, corresponding to this x value. So once I have the inflection point, I have everything that I need to graph our function. So when I put in a y and an x-axis, I can first plot our horizontal asymptote at y equals 1. Plot our two vertical asymptotes at x equals 2 and x equals negative 2. Now I'm going to plot the points that I found. One of them is at 0, negative 4, one of them is at 1, negative 3, and another is at 4, 0. And I'm going to draw what our graph looks like according to our intervals of increase and decrease, and our intervals of concave up and concave down in between the bounds that we found. And our graph is going to look a little something like this. Now when I plug our function into a graphing calculator, I'm going to get something that looks almost exactly like the function that we drew. Except here you can see a little bit more of that inflection point at 5.7034. Thank you for watching this video, and I hope you learned something about curve sketching.